Morning, everyone. I'm gonna start our 7th discussion in a row. Well, I think it's discussion 8, but we had that one with mock interviews that doesn't count. So we're doing an exam review, which is the second part of the exam review, and that is going to cover trees, including the balance trees, and heaps. Let me start the presentation. There we go. So as always, if you have any questions, ask them in the chat. We're gonna have some Menti problems throughout the presentation as always. And now I'm gonna start. So we're gonna cover trees and traversals, which is gonna include terminology, types of trees, all traversals, including the level order, insertion, deletion, and search into a binary search tree, ways of implementing and representing trees and their performance. And then we're going to go into balance trees, which are going to be our AVL trees, red black trees, B and B plus trees, and splay trees. This part, I don't think you'll be asked any pseudocode related to these in the exam. And then heaps, we're going to cover the representation, insertion, deletion, etc., and performance, of course. So trees and tree traversals. Tree is a data structure that consists of nodes, where each node has a value and a list of references to other nodes, which we call children. We have a little example of the possible structure of a binary tree in here. There are several type of trees that we study in this course, including their properties. So some examples are like general trees, so those can be n-ary. Binary trees with 2 children, binary search trees that are sorted, AVL trees, which are sorted and balanced, red-black trees the same way, splay trees, and n-ary trees, which we talked about. And then we have B and B plus trees. Moving on. There we go. Tree traversals. So we have, well, you know what tree traversal means. It's just visiting, the order of visiting nodes. So we have pre-order. So you visit each node first and then move on to its children, starting with the left child and going to the right child. We have in order, where you visit the left child first, then the node itself, and then you go to the right child. And then post order, where you visit the children first, starting with the left child and then going back to the node. And do you have any questions so far about the traversals? Real quick. If not, I'm going to move on because y'all know. If you're asked for a pre-order traversal, look for this line here. So going all the way left, you're going to have something like A, B, D, H in a row all the way to the leaf here. If you're looking for a post-order traversal, you'll have this line here at the very end, starting from the bottom. So you'll have G, C, A always. Moving on, binary search tree operations. So we have search, which is because binary search trees are sorted, it's you search through the tree by comparing the value you're looking for with the current node and seeing whether you have to go left or right. Depending on it, you have this function here for it. And then average time complexity is log n. But because it's not balanced, so you can have like a very heavily skewed tree, the worst case time complexity is still O of n. Inserting into a binary search tree, it works the same way. So you compare the value that you want to insert with the value of the current node. And if the value that you want to insert is greater, you go right. If it's less, you go left. Same as with search, average is log n, worst case is n, for the same reasons. Delete is works the same way. You're searching the tree for the value to delete, and then you remove it. And on top of that, you need to replace the or reconnect the tree once you remove some node. The code for it is given here. And because you've built a build tree, I'm pretty sure you're all familiar with how deletion works. After you remove it, you replace the node with either in order successor or in order predecessor. So successor is the leftmost node in the right subtree, and the predecessor is the rightmost node, well, the first right node in the left subtree, essentially. So balance trees, this is our Menti. I'm gonna stop this share, change to Menti. Where is my, it's here. Okay. The Menti code is 74351424. So I'm going to type it in the chat and wait for you to join. Okay, let's move on to the first question. Is anyone else going to join? No. Let's just, okay. I guess there are people still joining. Question number 1. What is the third node to be visited in or printed out in a post order traversal of this tree? Okay, yeah, that's good. Good job. Next question. What is the time complexity of deleting from a binary search tree in the worst case? Worst case. Good job. What is the time complexity of inserting into a binary search tree in the worst case? We're not having the leaderboard until I'm done with these questions. It's too distracting. We need to get through this review. Good job, guys. You did well. Now, what is the time complexity of searching a binary search tree in the average case? Yay. And now the leaderboard. Wow. This. Good job, everyone. And now we're going to go back to our slides. Share. Start presentation. And I don't. Okay. Moving on, avial trees. Avial trees are self-balancing binary trees. It'll be something like write pseudocode to insert or delete into or delete from an avial tree or something like that, Andrew. So avial trees are self-balancing binary search trees. So that means that at each insertion, it rebalances itself to create a bushy tree. Balance factors for all nodes should have the magnitude less than 2. So yes, the slides will be published, Liam. I'll also send them in the Slack. Magnitude should be less than 2, so it can be something like -1 or 1, 0, but it cannot be 2 or -2. So the way you calculate balance factor is you subtract the height of the left subtree or height of the right subtree from the height of the left subtree. And then since avial tree stays balanced, the insertion, deletion, and searching are all O log of n in the worst case and average case. That is because the height will always be the log of n. Balance factors are checked after each insertion and deletion, and if needed, the tree will be rebalanced itself. Well, the tree will rebalance itself with rotations. Just remember that the balance factor for this class will be calculated using the height of the left subtree minus the height of the right subtree. But doing it other way around is also acceptable in general. So if you encounter that case, it is correct. Red-black trees we have. It's an alternative to avial trees. C++ map is implemented using red-black tree. It is used for scheduling algorithms. Binary tree that balances itself. So red-black trees also balance themselves automatically, but they do it using 4 rules. And those are node is either red or black, obviously from the name, which they didn't inspire Deadpool's uniform, just so we're clear on that one. The root is always black. Remember that one? Root is always black. Red node always has black children. So a red node always has black children. Black node can have black and red children. i.e. red nodes cannot have red children. Black nodes can have either red or black children. Null references are always considered black. So null node is a black node. And number of black nodes is in any path from the root to the leaf is the same. B trees. B trees are also self-balancing. They're technically n-ary trees. They're designed to store very large amounts of data for very fast query and retrieval. B trees can have multiple key value pairs in a node, sorted ascendingly by keys. And just give me a second. Okay. And I already said there are n-ary trees where each node has up to n children at each stage. So all nodes have at most n children. Root is either a leaf or has 2 to n children. So it can have between 2 and n number of children. Internal or non-leaf nodes have a ceiling n over 2, which is like integer division, but going up higher instead of the lower integer, if that makes sense. You all know what ceiling is. Non-leaf or internal nodes have a maximum of n minus 1 keys. So if we have order 4, which means that n is 4, each of these can have up to 3 keys. L is the maximum number of keys items a leaf node can have, so that's 4. B plus trees are like B trees, but the all the unique values are in the leaf nodes. So every internal node is basically just a duplicate of some value in the leaf. And leaf nodes only contain keys. All data is stored there, and additional level is added here at the bottom that connects all the leaf nodes in basically a linked list. So the differences between B and B plus trees is in B trees, data can be stored in leaf and internal nodes. B plus trees, data is stored only in leaf nodes. Searching is a bit slower in B trees as opposed to B plus trees because you have access to all the nodes at the bottom. No redundant search keys are present in B trees, but because you have the duplicates between the leaf nodes and the internal nodes, you have some redundancy there. In B trees, deletion is complex. In B plus trees, it's easy because you can do it directly from the leaf nodes. And in B tree, leaves cannot be linked together. This is going to be valuable for you to have on your cheat sheet for exam, just so you know, just this table. It's going to be good, as well as the rules for red black trees. Moving on, splay trees. Splay trees are also self-balancing binary search trees. After each node is accessed, it's moved to the root via like a zigzag rotation. So it doesn't necessarily flip, but you do like zigs and zags to alternate to create bushiness. That's what I want to say. So this is best for ensuring that the most commonly accessed nodes have the least access time. So if you have your nodes like this, the values that you're working with organized like this, and then you keep accessing only 1 and 6, you'll have to go through a single node if you want to access 1 and 2 nodes at max if you want to access 6. So it's like you have these nodes at the top that are very commonly used, and you lower the access time of those nodes. Back to Menti, we have questions about balance trees. Okay. Same access code, everyone? Okay. Let's move on. What will be the root of the AVL tree after you insert 5, and that means after the rotations? Okay, good, good job. So what type of imbalance can be seen here? Think about the node that has the balance factor of 2 in this case. And start from there. This one was a little rough, but it is a left-left rotation because the node with the imbalance is the root node and it has the 2 left nodes following it. Next question. How many rotations will it take to make this tree balanced? Yeah, so the solution is 4, even though 3 does kind of make sense, but you have to start at the bottom and then go up and balance at each level. So it's going to take like 1 more to flip it to a properly bushy tree. And then red black trees. This is going to be a true or false question, guys. Are self-balancing binary search trees? Are they or are they not? Yes, good job. Next question. The root of a red-black tree can be any color. Good job. It can only be black. Next question. Number of red nodes from any path from root to leaf is always the same. Yeah, so this one's false because this applies to black nodes. Back to leaderboard. Okay, good job, good job. Oh, wow. Who is, okay, I know. Endrit, that's you at the top. Good job. That you're doing great this discussion. Back to slides. Share. Okay. So heaps and priority queues. A priority queue is a special type of queue in which each element has a value and a priority. An element with high priority is dequeued before an element with low priority. If 2 elements have the same priority, they are served according to their order in queue. So if 2 elements have the same priority, they behave as a regular queue elements. Functions, we have insert, inserts an item with a given priority. Peak highest priority, or peak, it's going to return the item with the highest priority. Pop, it's going to pop off the highest priority item. And depending on the implementation, you can do the same thing. So same operations with like lowest priority. But at the same time, I think it's just like, it's still high priority. It's just you prioritize different things, if you get what I mean. Anyway, binary heaps are ways to implement, since priority queues are an abstract type. Heaps are what implements priority queues in reality. So a binary heap is a complete binary tree. Complete, guys. We need to remember that one. That satisfies the heap ordering property, which means that all the nodes, every node has a higher priority than all of its children. So depending on whether you're building a min heap or a max heap, for a min heap, all the children of every node are greater than that node. And if you're building a max heap, all the children are smaller. So it's the priority. If in a mini heap, root is the smallest element, in a max heap, root is the largest element. And only the root can be removed. So you, depending on whether you have like a mini heap or a max heap, you do extract min or extract max. And the removal operation is always O log of n, because it takes O of 1 to get the value that you're removing, because it's always the root. You just remove the root. But then when you're removing the root, you also have to do the heapify, which is log n, to ensure that you have a proper heap after you remove the element. And then with insertion, it's the same thing. You always insert at the end, but then you have to heapify up, which is O log of n. And then examples of min heap and max heap. Array representation, which is one that you'll be using most of the time. Every node at index I has a left child at index 2i plus 1 and the right child at 2i plus 2. And any node at index I can find its parent at index. You need to floor this, but it's I minus 1 divided by 2, and then you floor it to get the integer division. This table is going to be useful on the exam too. But I don't think you're going to need the one indexed array, because we use C++ arrays, which are 0 indexed. But anyway, you can have this table on your cheat sheet. Heap insertion, here's a little algorithm. I would advise you to follow this specific algorithm and not the one from the slides I think Professor Aman has, and I'll show you why. So if the heap size is 0, you just insert the new value at 0, and then you increment the size to have a 1. But if the heap size is not 0, you want to increase the size first of the array. So if you had only these elements here, so 5 through 28, you want to increase the size of the array so you have one more slot, and then place the value you want to insert at that last slot. And then you use percolate, which is heapify, up to arrange or rearrange and organize the heap. This is the example of a percolate up function. You keep going up until the parent is, well, as long as either the index is within bounds, and it's not mentioned here, but it should be. You cannot like access -1 as an index. Anyway, as long as the parent is 0 or above, and the parent is greater than the child, sorry, for a min heap, you need to swap the parent and the child and then call percolate up again. Then you keep going, swapping. And once you hit this, don't forget that if we ask you on the exam for this, don't forget to have that terminating. Yes, Sai, that is correct. You're about the pseudocode? Yes, that is how we would ask you to write pseudocode on the exam. So if you need to write pseudocode in the exam, don't forget to add the terminating condition for parent or child being less than 0. And then this is, I think, what Professor Aman has for the on his slides. You need to swap these two, because in the case that you have, like, this doesn't have the initial condition either for 0, but if you swap it, it's fine, because suppose that you have an empty heap which has the size 0. If you try to do this, this is an error out of bounds, because you're trying to access an element at -1, and you'll get a bunch of errors. It's like it doesn't give you the right values. And even if you had a heap with size 5, you'll just be replacing the last element instead of adding it into the heap. So swap these two. Yes, Nico, you can use C++ on the pseudocode questions. So increase the heap size and then do heap at size -1 is inserted value, and then you do the percolator. And here, once again, make sure that you have the terminating condition of parent index is less than 0. Deletion, you swap, well, you put the last element at the top. You save the top element first, because you have to return it after deletion. And then you decrement the size of the heap. So you're basically just cutting this element out. And then you do percolate down, and then here's the function. There's a lot going on here. This one's a lot longer. And delete works basically the same way for min and max. It's just that percolate down is gonna have, or heapify down is gonna have swapped signs here. That you have to think about that. Like, do I want the child to have a greater value or a smaller value, and write the pseudocode that way? And there's a participation activity that I'm not gonna go over right now. I'm gonna go over the sample rubric real quick, and then we'll move back to Menti. So, sample rubric for the exam. Yes, you will have to write code for heapify down and drift. So a sample rubric for a question in the exam is going to be a pseudocode question. Each pseudocode question is going to be 10 points total, and then we'll have 7 points for positive for correct pseudocode. And then you'll lose a point if you don't have a base case to return null pointer, for example, depending on what kind of question you're given. Invalid parameters passed into the function or method. General small errors in code, or if your pseudocode is too similar to English, that's going to be a -1, and then no return statement, or an infinite recursion, and -2 for bad recursive call or whatever. And this is just a sample, so don't there should be about 3 pseudocode questions as far as I'm aware, Seth. Yeah, you'll be fine. It depends on this is just a sample. We usually have, our rubrics usually have something like, if iteratively, use this rubric. If done iteratively, use this rubric. If done recursively, use this rubric. And then some of the questions might ask you for computational complexity, which you will have to include the complexity and correct explanation. And some questions might not. Some question might just ask you to write pseudocode, and that will be the 10 points. Okay, before we move on to Menti, Do you guys have any questions other than the ones you already asked?
Can I ask something about the pseudocode time complexity?
Yeah.
For example, if they ask the time complexity in insertion in a BST tree,
Mhm.
of course, usually it's asked for the worst case scenario, and we know that the insertion is like ON in that case in terms of we go. Do we have to explain every step of that pseudocode, or we just write?
Yes, because pseudocode is something that you'll be writing. How do I say this? You'll be solving a problem that is unique to this exam, and it's unique to you. So we want to see that you are able to read your own code, read any code at that, and tell us, what is the complexity of this. So we want to see every step, like these are all the contributions to the complexity. I call this function here, and this function has this time complexity, so it contributes this. Within this function, within this loop, this is how it gets to. Basically the same thing that you did on your um on your project 1 documentation. You just don't have to like you'll have less to less functions to work with than the project. Liam, send me your email if you want to join our channel for this discussion too. Do we have any more questions? Andrew, did I answer your question? I like zoned off. I was reading the chat while answering.
No, it's just that when I asked you earlier what kind of pseudocodes should we expect for trees, and you said that maybe you should do something like write a pseudocode on how you insert or delete or search, whatever it is, an element or a node in a BST tree. But basically, that's kind of a standard pseudocode, and that's why I asked, should we just write like ON? Because however you spin it, if you write a pseudocode to insert an element, for example, in a BST, you might have a bunch of O1s, but at the end, it's going to be like ON at the worst case scenario if the tree is like skewed all the way to the right, all the way to the left.
Yeah, it's just that sometimes when you write your code might not have like the worst case time complexity that we talked about. It might be worse. It just like it really depends on how you implement it.
Yeah. So, for example, if we do implement it like the pseudocode that's in the slides, basically that would be ON.
Yeah, then it should reflect the same time complexity. You still want to explain why, like
Yeah.
what is going on, but yeah.
But yeah, just to clarify, just to know what kind of question should we expect. For example, if there's a question to insert an element on a BSD tree, it's just like write the pseudocode, or there is a specific problem that we should solve writing a brand new algorithm from scratch.
It really depends on how they phrase the question. Some of the questions are, they give you the scenario and they're like, oh, this problem requires you to write this, and then they say like write pseudocode for this, right? It's going to be something that we've talked about. It's not going to be something brand new. It's not going to be something that like you'll have to figure out from scratch. It will definitely be something that you can use information from slides and pseudocode from slides for.
Okay.
The only thing is that like when I took the class, for example, it was the same way. It's just that I did not write the pseudocode from slides anywhere on my cheat sheet. Actually, I don't think we had cheat sheets when I took it. So I literally had to come up with everything from scratch. But it's gonna be easier if you write down a few things for 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 these. And Alex, your question about deleting from a B tree, I am not entirely sure. Like we don't talk about it in this review, so I don't think so, but it might be a good thing to like write down somewhere because you do have that little cheat sheet that you can make. Okay, moving on with yes, you can have anything. The cheat sheet can have anything as long as it's handwritten. Ricardo, you can draw on it if you want. So, Menti question. This you are presented with a perfect B tree and N is 3, L is 5, height is 2. How many unique keys are in this tree? Remember that it's a B tree, not a B plus tree. Seth, I think the cheat sheet is like one sheet of paper, but like both sides. So for this one, it's 53 because it's a B tree, which means that unique values can be in the internal node. So you have to add everything from the root down to the leaf nodes. And if you had a B plus tree, then you would have the 45 unique keys, which is just the bottom layer. But in B tree, you have to account for the top 2 layers too. Next question. What was the last element that was accessed in this display tree? Okay, great. Good job. This is a good result. Let's see. Oh, Andrew, you are still at the top. Good job. Good job. I'm gonna start. I think you're gonna have to have them printed out, Ricardo. I'm pretty sure you can write them on your tablet, but you'll have to have them printed out. I think that's what, because we're using honor lock. I think that's what honor lock will require. Yeah, I'm pretty sure it is allowed. And the last question. Well, actually, no, it isn't the last question. What is the array representation of the following heap? I probably should have given you more time for this one, but it's okay. Yay, good job, guys. Ah, that is not what I wanted. Sorry about that, guys. That was complete accident. In the insert operation on a binary heap, where is the new node initially inserted? So before heap 5. Yay, good job. Next question. In the delete operation, which node is always deleted? Yay, it's the root. Good job. Next one. What is the worst case time complexity of adding, deleting an element 2 from a heap? This question, I should have read it one more time. It's supposed to be what is the worst case time complexity. Good job, guys. Next question. Why did it? Sorry. Consider an array with n elements. What will be the time complexity of building a heap based on inserting all of the n elements into the array or into the new heap? Oh, yeah. Oh my God, that's amazing. Good job. And last question before I share the access code for the participation is, are you ready for the exam one, everyone? Take a good break before the exam. Long sleep. This is great. So take a long break. Don't overwork yourself. And good luck. And now I'm going to share the access code for the participation quiz.